Hey guys, welcome to my presentation. Today's topic is going to be standard univariate discrete distributions. So before that, I want to introduce myself. I'm Sai Krishna. I'm a student who is currently pursuing data science bachelor's degree at IARE. What are the objectives of this presentation? First is introduction. Next, types of different distributions which comes under the category of univariate discrete distributions. Then exploring each distribution briefly. The introduction. Okay, these are like prerequisites. First, you have to understand what is a univariate and what is a discrete distribution. Univariate, a function with only one variable is called univariate. Uni represents one, variate represents variable. Discrete distribution. A discrete distribution is one in which the data can only take on certain values. For example, integers. A continuous distribution is one in which data can be taken in any value within a specified range, which may be infinite. So what is a univariate discrete distribution? These are collections of distributions where data is discrete and functions have only one variable. Primarily, these are probability distributions. The class of discrete distributions can be defined as having a cumulative distribution function that is a step function with only a denumerable number of steps. According to the definition, the class has a considerable variety. Lattice distributions. Most of the discrete distributions used in statistics belong to a much narrower class, the lattice distributions. In these distributions, the intervals between the values of any one random variable for which there are non-zero probabilities are all integral multiples of one quantity. Point with these coordinates thus form a lattice. By an appropriate linear transformation, it can be arranged that all variables take values that are integers. For most of the discrete distributions that we will discuss, their values taken by the random variable cannot be negative. There are a number of ways of classifying non-negative lattice distributions. Classification into broad classes helps us to understand the multitude of available distributions and the relationships between them. The mere number of distributions in a class is not in itself a measure of importance. What is important is the inclusion of a wide variety within a specific class, with emphasis on the existence of special properties that apply to all members of the class. Constructing the models and further derivation of methods of analysis by analogy with known techniques for closely related distributions. Power series distributions. The term power series distributions is generally credited to Novak Kosambi, and Novak showed that many important discrete distributions belong to this class. They also investigated its moment and cumulant properties. The definition was extended to multivariate distributions by Hartree in 1959. Patil in 1961 allowed the set of values that the variate can take to be any non-empty enumerable set S of non-negative integers. Patil called this extended class generalized power series distributions because we are generalizing it with using non-negative integers. Estimation and other properties of GPS these have been explored further in Patil. Now let's discuss about Katz's family. A detailed study of a simple relationship, it was undertaken by Katz in his 1945 thesis. This system of distribution is known as the Katz family. The restrictions on the parameters are a is greater than 0, beta is less than 1, where beta greater than or equal to 1 does not yield a valid distribution. If alpha plus beta n less than 0, then Pn plus j is understood to be equal to 0 for all j greater than 0. Essentially, until and unless one sees the formula, will not understand it. Let's wait for that. Cats showed that there are many three possibilities over here. Okay, now where beta can be less than zero, the outcome is the binomial distribution with n cube by p. Beta is equal to minus q by p, or all the stuff. But when beta is equal to zero, the outcome is the Poisson's distribution with a to be equal to theta. But when beta is lying between 0 and 1, the outcome is the negative binomial distribution with a is equal to kp by p plus 1, beta is equal to p by p plus 1, that is k is equal to a by beta, p is equal to beta by 1 minus beta using the parameterizations. So the formula, the PGF of the Kx formula is given and the FMGF is also given. Next turn is Sandhat and Jewel's family. Sandhat and Jewel in 1981 with Wilmot 1988 have studied the Sandhat and Jewel family of distributions. Their interest lies in actuarial applications. So many of their papers are in actuarial journals. The family is a modified form of the cat's family. The recurrence relationship for the probabilities is this. So px plus 1 by p of x is equal to a plus b plus ax by 1 plus x, where x is 1 comma 2 comma 3 and so on. Taking alpha to be equal to a plus b, beta to be equal to a shows this is the same as the cat's relationship for all x except for the inclusion of x is equal to 0. The PGF for the Sandhat and Jewel family has the form g of z is equal to c plus 1 minus a. This formula is very important here, and h of z is the PGF for a cat's distribution. Now, distributions based on Lagrangian expansions. Distributions belonging to the wide class of Lagrangian distributions are based on Lagrangian expansions. Given the transformation z is equal to ug of z, Lagrange 1736 to 1813 gave two different expansions for functions of z in terms of w. These led to two families for Lagrange distribution, LD1 and LD2. Suppose that g of z is an analytic function of z such that g of naught is greater than z and g of 1 equal to 1, and it is not necessary for g of z to be a PGF as was at first thought, provided that it satisfies these conditions. The smallest non-zero root of the transformation transformation z is equal to g of z yields a PGF with the following Lagrangian expansion in powers of u. So this essentially gives the explanation and summarizes the Lagrange distribution. Next is our own favorite binomial distribution. Okay, so the binomial distribution definition is where so we all know the definition. So the binomial distribution can be defined by using the formula as the distribution of a random variable x, for which p of x is equal to n by ncx is ncx, p of x into q of n minus x, where x belongs from 0 to n. So here q plus p must be equal to 1 because q and p both represent probabilities of a different direction, and they must be equal to 1, where p and q are equal greater than 0 since they are probabilities, they cannot be less than 0. Occasionally a more general form is used in which the variable x is transformed into a plus b of x, where a, b are real numbers with b equal to 0, where n is equal to 1. The distribution is known as the Bernoulli distribution. The characteristic function CF from the binomial distribution is this, and the probability generating function is this. And we all know the other properties. Yes, we all know that. So the properties, the binomial distributions belong to a number of families of distributions and hence possess the properties of each of the families. It is a distribution which finite support as defined. It consists of n plus 1 non-zero probabilities associating with the values 0, 1, 2 and so on. So these are certain properties of binomial distributions. Now let's come to applications. The binomial distribution arises whenever underlying events have two possible outcomes. That's why it is binomial. The chances of which remain constant. The importance of the distribution has extended from its original application in gaming to many other areas. Its use in genetics arises because of the inheritance of biological characteristics depends on the genes that occur in pairs. See, for example, Fisher and Mather's analysis of data on straight versus wavy hair in mice. Recent application in genetics is the study of the number of nucleotides that are in the same state on two DNA sequences by Calfan and Risco in 1982. Seber in 1982 has given a number of instances of the use of binomial distributions in animal ecology, for example in Mach aperture estimation of the size of an animal population. And etc. So we essentially are using binomial distributions in genetics as well as in ecology research purposes. Um, Thank you for being with me. It's been a great time. So, what we have learned. So, before that, let me summarize what we have learned. First, we have introduced about what is an univariate, what is a discrete distribution, what essentially is a standard univariate discrete distribution. Then we go on to classify each and some of the important distributions and know about them briefly, such that we have come till here. Um Thanks for listening this presentation. I hope you have learned a lot. Thank you. Have an